Okay. Hi, everyone. My name is Austin Ward. I'm going to be giving this talk today on distributed systems, the case for space. What that essentially means is distributed systems are distributed, so spread throughout space, and why I think that distributed systems are important. So a little bit about me. I'm a Binghamton alumnus. I graduated from Binghamton back in 2018. I was also previously an organizer for HackBU. And I've been with Capital One since I graduated back in July, before July, back in May, but of 2018. I started working back in July. So since I've graduated and started working at Capital One, I've worked on a couple of different parts within Capital One. I originally worked on backend APIs within Capital One's small business bank part of the company. After that, I started working on clickstream data pipelines. Then I went to the Insights platform. Insights are similar to features. They're a little bit broader in their nature, but we found that migrating away from them was best for us. So we then moved into what is now known as the feature platform, and I work on the orchestration portion of that. So up in the top right, you can see us at Capital One at HackBU's at last year's HackBU, where Capital One attended, and then my cat Lucy, who always gets her tongue stuck out of her mouth, and then my dog Friday, who doesn't let me code unless she's sitting on my lap. Okay. So a little bit of an overview here. What I'm going to be talking about today, these are the topics. What is a distributed system? Example technologies. Why should I care, or you rather? Then distribute everything, right? Well, not necessarily. Personal experiences with distributed systems, to distribute or not to distribute, and then resources and recommended readings. So first, definition. A distributed system, also known as distributed computing, is a system with multiple components located on different machines that communicate and coordinate actions in order to appear as a single coherent system to the end user, right? Well, first off, right off the bat, think of some distributed systems that you interact with daily, right? Facebook.com, or Facebook is just Facebook. You go on Facebook, you don't have to worry about, if you're connecting to the right server or whatnot, right? Twitter is another great example, or Capital One's backend when you're connecting to your banking information. All these systems are distributed, but you're not aware of the fact that they're distributed, right? So hiding that information from this front end user, looking like a single coherent system. I think another really important topic from this definition is communicating and coordinating between the different machines. We're going to talk about that a little bit further and what that means between these different machines. So distributed systems come in many forms. Some examples are a cluster of nodes performing work together. This basically just means any number of machines that are performing some sort of computation or workload together. Auto-scaling API that uses a shared database, right? So the database itself might be distributed as well, such as DynamoDB or Cassandra. But let's say, for instance, you have a number of containerized, let's say you have a containerized API and a number of those containers spun up and all accessing, making read and writes to the database at the same time. You might have cross-region availability with active-active. So you might have East and West, United States, East and West. You might have your API available in both of those, and those are active-active. All these are examples of distributed systems, right? And to dive in a little bit deeper there, a distributed system doesn't have to be like this massive distributed system that you see on the right here, which is a distributed system, by the way. And this is absolutely insane. This is a really great distributed system with fault tolerance and availability and everything built into it. But what we see on the left here too, this simple system with a load balancer and two apps running at the same time of the same application that are both connected to the database server. This is also a distributed system. So you can start, typically what you'll do is you'll start with something on the left and build your way up to something on the right. Not necessarily, but I found that it's a little bit easier to break things down and eat it in chunks when you think about the system as something smaller and then build it up from there. But both of these are examples of distributed systems and everything in between them as well. So some example technologies, right? You have Cassandra here, which is a distributed wide column management system designed to handle large amounts of data. Basically, what this means is Cassandra is a distributed database that is built to handle big data, right? Think about the data that you need for creating like a machine learning model at the enterprise level, right? You're probably going to have a lot of data that's going to go into that, and Cassandra is a really good host for holding all of that data. Another example is etcd. This is an open source distributed key value store. It's used to hold and manage critical information that distributed systems need to keep running. Kubernetes is an example of one of those distributed systems. Kubernetes is an orchestration, is a container orchestration platform, essentially. It's portable, extensible, and is great for containerized workloads and services. All of these are examples of distributed systems, and there's a bunch that I'm leaving off this list as well, just to give you sort of an idea as to what it means, right? Okay, so why should you care, right? Well, a couple of reasons. Better availability. If there is no single point of failure, then a small amount of failure is acceptable and expected for, with that being said, right? So let me talk a little bit more about that, right? No single point of failure. So let's say, for instance, back at our load balancer example here, right? So if one of these apps were to go down, then the other one is still available. Our load balancer now will just route traffic to that. And it looks like everything is still working correctly, right? The server might be a little bit overloaded at the time, but hopefully it can handle most of the traffic. And partial availability is better than no availability. So anyways, so better availability, right? That is definitely an added benefit. And it means that your app is still up and running, even though part of your infrastructure or a piece of your service has failed, your application is still running and doing what it's supposed to be doing. Another added benefit here is that it helps to hide the time that it takes to fix or replace unhealthy nodes, right? So again, back to this example, if this server were to go down and the server is up and running, the user who's using our app doesn't know that, you know, we currently have less ability to service our users. And we can either automatically, preferably automate the process of spinning back up a node in its place for the failed one, or it gives us time in case that's not possible to go in and manually fix a node and spin that back up and get our service back to the 100% capacity that we want it to be at. It's also better durability. This mainly pertains to to distributed databases. Continuously makes copies of a piece of data, right? So again, another great example here is Cassandra. When Cassandra is done right, and that is hard, by the way, but when Cassandra is done right, you have multiple copies of a piece of data within your cluster stored on different nodes. So if one of those nodes were to go down, you know that your data is safe still. And this is true of any node, right? So making sure that that data is durable is something that's really important here. Another great example is scalability. So I think an important concept here is horizontal scaling versus vertical scaling. So if you're unfamiliar with this, horizontal scaling basically means, let's say, for instance, that we have a compute resource that isn't really powerful, and then one that's super powerful. We'll say that this is 1x and this is 10x, okay? So horizontal scaling is the ability to spin up a whole bunch of these machines, and then vertical scaling, going back to that, horizontal scaling is the ability to spin up a whole bunch of 1x machines and have them work in unison, or in parallel, I should say. And vertical scaling is the ability to go from a 1x machine and scaling it up to a 10x machine or to a 100x machine, right? With distributed systems, you go with horizontal scaling, which is fantastic because it, one, allows you to meet the needs of your traffic better. It has real-time scaling to meet the traffic, to meet your traffic needs. And then it also has the ability to more efficiently meet the needs of your traffic, right? So let's say, for instance, we have a server that can handle 1,000 requests per second and one that can handle 100 requests per second, but we have 200 requests per second coming in. We could go with the 1,000 requests per second server and it would be able to meet our needs, but we would be wasting compute resources, and that's expensive. If we go with the 2 horizontal scaling servers that can handle 100 loads each. We're perfectly meeting our needs. And then we have the ability to scale up or down based on the amount of requests that we're getting, right? And that is a contrived example. You definitely don't want to be meeting 100% of capacity on both of your servers. That's bad. But anyways, there's also better efficiency. So what I was saying before, idle machines are expensive, right? To have that 10x server running and only using 200 out of 1,000 requests possible, it's expensive, right? So it's better to have a machine that is busy because it only costs slightly more than an idle machine. And then a little bit of mix between scalability and efficiency here is that we have the ability to scale down to avoid unused machines and keep other machines busy. The closer to 100%, the better. We don't want to reach 100%. Typically, what we do is based on CPU utilization of 80 to 90%, somewhere around there. If we're reaching those marks, we'll scale up, add in a new node. But that is essentially some of the benefits of distributed systems, right? So distribute everything, right? Not necessarily. Distributed systems are very hard to build and come with a number of their own problems, right? So it's higher cost right off the bat. You have more resources that you need to use. Those resources are expensive. It's going to cost you more money. And they also fail often. I'll talk a little bit about some of my personal experiences in a little bit, but these systems typically tend to fail more often, and it's harder to debug them as well, right? A really good example that I heard about this once is that it's really easy to debug something that has a couple of dereference pointers away compared to something that's a couple of switches away. So, excuse me. And then also with debugging, it's especially hard to figure out when something is slow, right? Like if you get the, the requests are like, oh yeah, when I make a feature job submission request, it's slow. Well, in a distributed system, it's going to be really hard to debug. You're not just looking at code, right? You look at the code, and then you also have to worry about the distributed nature of your system. Is there something that's between system A and component A and component B that's causing them to be slow there, or whatever have you? There's also coordination, which is extremely difficult. That is very challenging, and that's something that I'll talk about in a little bit too from my personal experiences. But getting systems to be coordinated and understanding consistency between different systems, right? If we have, I don't want to dive too deep into this because I talk about it, I think, on the next slide. Yeah. But anyways, coordination is very difficult, very, very hard. And then designing a truly distributed system with no single point of failure is even harder, right? So just to go back to this example, this system on the left here is distributed. And if app 1 were to go down, great, we still have app 2 and vice versa. But if our load balancer goes down, we're not able to get any traffic. That's a single point of failure. You'll notice for the example on the right, we have multiple load balancers. So how to have a truly distributed system without a single point of failure is something that's extremely challenging. And I mean, you can just look at this example on the right. It looks very difficult to build, and that's because it is very difficult to build. And make sure that you have consistency and availability and all of that. Like, building distributed systems is very hard, but they are extremely important. And I'll tell you a little bit why also. I mean, you can imagine why, but from some of my own personal experiences. So the first one that I want to talk about is a use case for Cassandra that we had. Cassandra is, again, just to cover this very briefly, is great for big data. And so when I was working on the Insights platform, we had Cassandra data centers in both East and West in our production environments that was handling about 1.5 billion insights per day. This was terabytes of data. And so when things went bad, they went really bad, right? When things broke, they broke, and it was hard to debug. If you have a node that goes down, that's the whole point of it, is that there's no single point of failure, right? But even designing it with no single point of failure is hard. And if a node goes down, you might have a couple of issues that happen, right? Maybe you're unable to automatically stand back up a node in its place, or that node going down causes cascading failures where node 1 goes down, which causes node 2 to go down, and so on and so forth. And then there's also backups, loading table backups, right? So I can recall a couple of times where having automated table backups is really challenging with Cassandra. A lot of the times doing it manually was the best option and the only option. So if we had an East Cassandra data center outage, we might have to do a table backup from west to east. And because of the size of the data, the amount of data, I mean, we were doing terabytes per day, right? That really adds up. And so these table backups or table loading from one region to another really took about 36 hours. And that's not like hands-on manually dragging files from one computer to another, right? Like obviously a large portion of that is automated, but still it takes 36 hours just due to the nature of the amount of data that we're dealing with. Now, I believe a lot of this was due initially to poor structuring, not really understanding how to properly set up our Cassandra system. And since then, we've been able to resolve these issues. Our Cassandra instances are a lot stronger now, and we haven't had nearly as many outages. We've had automated rehydration set up, and most of our node cascading failures have been resolved. But again, like that was a system that took a lot of production support and many engineers to fix. And you can imagine the cost factor of keeping this running and mistakes happening, right? I mean, it's a lot of data. Then to talk a little bit more about what I've been doing recently. So for the feature platform compute orchestration system, this is what I'm working on now. This is my day job. Just gonna move this so that you can see what's at the bottom here. I changed the slide. Okay, so for the orchestration system, we have some business requirements, right? We have to be active-active, which means that we're available in both East and West. Whether you hit East or West, our app should act the same, being that single coherent system to the end user. Another business requirement was 99.99% uptime. So we were allowed to be down for 52 minutes each year over a rolling 12 months. And then we can't be down for more than 15 minutes at a time, and we can't have an incident happen twice within a 90-day span. All right, so these are all business requirements that we have to meet in order to be a platform within Capital One. So how do we achieve that? Well, distributed systems. So Route 53 is a DNS service hosted by Amazon. This allows us to be active within both East and West regions. We use ALB scaling within both regions. So we will have scaling for our containerized API instances, which we should have, or we do have 3 instances, 3 containers running in all AZs within both East and West. And then we use DynamoDB as a distributed database. So there's no single point of failure in there, except Route 53, which if that goes down, probably so is half the internet. So hopefully that doesn't happen. But I don't even think that Route 53, I don't want to talk about this too much because I can't say for certain, but I don't believe that Route 53 has a single point of failure. So to distribute or not to distribute? Most of the time, it's probably better to build a distributed system. Most of the time, a distributed system will be better. But with that being said, right, I think a lot of it, there's a lot that goes into that, right? So you probably don't need a distributed system if you're not seeing a ton of traffic, if some downtime is acceptable and some data loss is acceptable, or you're iterating and changing quickly on ideas, right? Okay, so just an example here. Let's say that I'm building some application for my own use to track how many times I turn my lights on and off, right? Does that really need to be up 100% of the time? Like if that goes down, is that going to cost my business money? Or if I lose the amount of times that my light has shut off on and off between like a week span, is that really going to matter that much? Probably not. I really don't need to build a distributed system in this case, right? That would be super overkill. But also, a good example here, and I haven't worked in the startup field at all, but a company like Pinterest, for instance, when they were first starting out, they were iterating and changing quickly. They didn't need a distributed system. They needed something that could be a proof of concept. And so when they first started out, they had one machine and one database server, right? And that's totally acceptable. There was no reason to do more than that because they were iterating and changing quickly on ideas. But you probably should build a distributed system in most other cases. Most other cases, downtime and data loss are not acceptable. And if you have the resources to build a distributed system, you probably should build a distributed system. So That's my talk. Here are some resources and recommended readings. I cannot recommend notes on distributed systems for young bloods enough. That truly is a phenomenal read and honestly the inspiration for this talk. So I highly recommend you check it out. It goes into way more depth than I possibly could for this talk, but really hope you check that out. And then at the bottom here, the system design primer and system design section of TripleByte's Way Too Long Interview Prep Guide. Check out both of those as well. They're really great for system design, interview prep, really great reads. And yeah, that's it. Thank you very much. So I will be, this is a recorded video that I have really bad internet connection right now. So I just wanted to throw this up online in case I'm unable to give the talk if there's any issues. But I'm going to throw this up on YouTube. And then if you guys have any questions or anything, I'll be in the chat and we can talk there. Thanks.